AIP 5 and the topic is steering and Unity3D. So I will not give you that much introduction of Unity3D in this class because you know that one. So it is just in the heading, and then you will have some video tutorials. So our focus will be mainly on steering. So yeah, before asking you what is steering, this is the recap. We are looking for an intelligent agent, and we know that intelligent agent have some attributes. What are the attributes? It will have abilities, it will have goal and preferences, it will have some prior knowledge, and based on that it will have some perception. It will have observations and then past experience. It will do some actions on the environment based on these attributes. That is our intelligent agent, if you can remember. Okay? Then also just keep in mind this example of our robot, serving robot. Then if we go for domain understanding, this slide also you have seen before. There are 4 basic tasks here. One is modeling the environment. We define the environment, and we create some kind of knowledge base. And how to create knowledge base, or we got some introduction about this one. And then we will have evidential reasoning or perception in domain understanding, which will give us the observations and determine what the world is look like or something like this. And then third is action. Based on the perception or evidential reasoning, we will have some action on the environment. Our intelligent agent will have some action on the environment. And then last one is learning from the past experience. So our focus in this lecture is related to action. How to do action on the environment. When we talk about steering, we're actually talking about mostly focusing on the action. Okay? So then what is steering? To understand this one, first see an example and then example video, and then we will discuss this one more. Just look into the writings also. That's it. So when you look into this video, what is this car doing? It is using some kind of knowledge or artificial intelligence to follow a path here. It is changing the speed. Sometimes you can see that it is faster, sometimes you can see that it is slower. It is changing the direction, and there is a line here which is showing the direction, the way it is looking. I mean, the way it is looking forward now in this way. So and also when the path is changing, how it is behaving, something like this. So when a car is moving and following this path, then this car is using some kind of force. This force have two things. One is it has a speed, and then also it has some direction changes. So the speed, you can say, for example, the maximum speed is, let's say, 5 pixels per frame. I'm telling pixels because in computer screen we talk about pixel normally. You can tell this one as distance in meter or something like this also. But let's say this car is moving 5 pixels per frame. So when you are showing this frame in the computer, in the next frame, the car will be 5 pixels apart from the previous place. That is the idea. But what will be the direction? That will be set by steering behaviors. So an intelligent agent need to know what kind of steering behavior it should follow in its next step. It is not only for car movement, it can be for our serving robot when it is finding the path. It can have many other applications. So that is the idea of steering. It needs to know which direction it will follow. That is the thing. Do you understand that? What is the basic idea of steering? Okay. Then, yes. If we talk about steering behavior, then actually to understand that one and to reflect this one on an intelligent agent, the steering behaviors, we need to have some understanding about coordinate geometry, vectors, matrix, and physics. So we will apply some of these concepts to them to understand steering behavior. I will not go to the basic concepts. I will just show some application. Okay. So when we are talking about steering behavior, what is the context of steering? When we have an autonomous agent, it has three things. Action selection, it will first select the action based on its goal, and then it will have steering. For example, there is a vehicle here and the target is going there. Then it will have, it needs to select that. For example, it is looking like this in this direction, but the target is there, so it needs to move. So these are kind of action selection based on the goal and strategy, something like this. Then it needs to move. So you have to apply some kind of force which will move that one. This is we are telling about steering. Here we are telling about steering. In steering we calculate the force, which direction it should go, how much force will make that direction, something like this. And then we have locomotion. In locomotion, it is actually the practical thing. The device is moving because of that force and then going there. This is locomotion. So in computer, when you show in this kind of screen, we are not moving a physical object maybe. We will show this one by animation or some kind of articulation. That is the idea. So this is the context of steering. Now to describe the steering behaviors, we need to take an example. Let's say this vehicle model. So this example I took from a paper. You will get the reference maybe in the next slide or 2 or 3 more slides later. So we have a vehicle. That vehicle can have thrust, and then it can have braking, it can have steering. So braking will slow down, thrust will speed up, and then steering will put the direction, which way it will go. And what kind of attributes we can put in our programming so that we can model this kind of vehicle. And then we will put some kind of, calculate some kind of force based on the current position and the target, and then move that vehicle towards that direction, and then run that vehicle or animate that vehicle from going from one direction, one place to another place. How can we do that? We can have multiple variables. For example, the vehicle can have velocity, it have current position, it can have velocity, it can have mass. Based on mass and force, you can calculate the velocity, because if the mass is high and the force is low, the velocity will be less, something like this. and then the coordinates or the coordinate system it is now having, and then also I think you have some experience on image rotation and something like this in image processing, isn't it? So in image processing, when you rotate the image, then you always think about some kind of coordinate system based on which it is rotating. So that kind of thing you have to consider here also. Then time delta is, for example, another variable. It can show the difference between one frame to another frame. As I told you, that a vehicle can have a speed of 5 pixels in each frame. So one frame to another frame in time maybe 30 frames per second if you consider. Then in 1 second you are actually moving 30 frames. So these are the complications, or the when you are considering the calculation, you have to consider. Then what will be the maximum force the vehicle can have? Because if you make a robot or intelligent agent, something like this, which can move, of course it has a limitation. It cannot unlimitedly push it using a force. So it will have a maximum force and maximum speed limit also. So these are the things a vehicle can have. And we can put these things with some kind of values in our programming. That is an example of a simple vehicle model. Then what kind of physics it can reflect? Let's say acceleration. How much will be the acceleration? It is based on the force and its mass. These are just actually normal mathematical calculation, and in some places, for example, here I didn't define the thing directly. It is just example of programming function you can use, and then you can define those functions by your own way, depending upon your intelligent agent, what kind of agent you want. Okay. Just say here, if you consider velocity of something, how many dimensions of that attribute have? Velocity. Is that a scalar or vector? Velocity? It's a vector. It has two things, isn't that? One is the speed, another one is in which direction it is going. So we know that scalar have only value, but vector have a value and then a direction. So when you consider velocity, it is actually having two things, the value and the direction. The value is the speed of the car, for example, or speed of the vehicle, and then direction is which way it is going. If my target is there and if I am the vehicle, then if I move in this way, so my velocity is in this direction, maybe 5 pixels per frame, but I have to go in this direction. And how to find out these things? That is the challenge in steering, defining the steering behaviors. So these are just simple math. And then I just put one line here, applying banking to fake it. For example, you are having a vehicle here, the target is going here. And then your current velocity is in this direction. But you cannot go in this direction, your target is here, so you will go in this direction. So you are putting a force in this side, and then this force is eventually making you going there. But you see here, it is looking like this, and then here it is looking like this. So if you have a car, for example, or vehicle, and if you want to animate this one in the screen, then how can you show that it is moving from this direction to this direction? You can apply kind of image rotation algorithm to show that the vehicle is moving like this. Instead of doing this, you can save some templates, or you can save some images of the car, when in this direction how it looks like, when in this direction how it looks like, and then more realistic images, and then just apply those things. When it is in this direction, just take that template from the back. In this way, you can depict something. So this is just a side issue I was telling, and that's why we're telling that apply banking to fake it. Sometimes we just fake it instead of rotating it. Okay? So this is the physics related to the model. So we have a vehicle model, this one, with some attributes. What can be the attributes? Is that limited? No, this is not limited. You can define your own attributes. This is just an example. Okay? And then some example of physics rule related to this one. Okay? Do you understand until now? Everything clear? Good. Then we are going for some of the steering behaviors. We have that vehicle model, and we will see how these steering behavior actually looking like. And I will give you some hints related to the implementation, and you will have some video tutorials how to implement this one in Python. And then I think hopefully that will help you to learn these things nicely. Okay? So there are many steering behaviors available. One of the very well-known paper related to this is Reynolds paper, and he actually defined these steering behaviors. If we have an intelligent agent that can move, then what kind of steering we can put on that one? It is not always, you don't have to say that it is only vehicle. It can be a human being in a Hitman game. He is moving, and which way he will move, something like this. So these are some of the examples of steering behaviors, which are simple behaviors. I mean, not complex or not combination of multiple behaviors. We are telling these are simple behaviors. Seek and flee, evasion and pursuit, wander, arrival, something like this. We will go each of these now, one by one, okay? First is seek and flee. So this is our vehicle. You can just imagine this one, okay? This one in this place, this green dot in all of the images I'm going to show you. Okay, so we have this vehicle here, and we want to define what is seek and what is flee. Seek means you have a vehicle and you have a target, and this vehicle is going to go to the target location. The current location is here, target location is here. It has some kind of velocity right now, and it is, for example, going this way. These are all examples, okay? It is going this way, but we have to reach this position. And when the vehicle is trying to reach this position, we are telling this one seeking. And for example, you have a target here, and you have the vehicle here, and the goal of this vehicle is to go away from this target location. Then we are telling this one as flee, which is opposite of seek. So is that clear? Flee and seek. Good then. So how to do that? This seek and flee thing. Just to give you some hints about this, we have, for example, one vector v1. We have another vector v2. If we sum up these two vectors, what will happen? Something like this. It is just, I am reminding you the vector geometry again, okay? Then, if you just subtract v2 from v1, what will happen? This is summation, but what will be the case for subtraction? It is just a v1 plus opposite of v2. That is the thing. Then this is the answer. So this is basic vector geometry. Then how we will find the steering behavior in seeking for this vehicle when it is in this position, the current location, and the target location is this one. It is our vehicle, it is our target location, and this is our current velocity. So current velocity is showing this direction with some kind of speed, but we have to go to this direction with some kind of speed. That is our problem here in seeking. And when you go sit down in your computer for programming, that is the problem you have to solve. To show that something is seeking something else. So how to do that? We have this desired vector, and we have this current vector, which we have now, okay? And we have to find out this one. So just this is, we can tell this one as the steering. I mean, our steering will set which direction it will go in which speed. Our desired steering, desired velocity is this one, but our current velocity is this one. Steering velocity will be like this. The force we have to calculate for steering, it is from this one. It will come from this one. How? So steering is actually giving us desired minus current velocity. Desired velocity minus current velocity. That is the vector calculation. So you have some speed and you have some direction. You have some speed, you have some direction as the target. Just subtracting one from another will give us the steering speed and steering direction. To understand this one more mathematically and how to code this one in Python, you will have a very nice example here. Okay? So we have seek and flee behavior, and how can we calculate from this place to this place? It is based on this vector geometry. So, and you will get an example here, very nicely shown about Python development in this case. The next two behaviors are evasion and pursuit. So what is evasion? You have your vehicle here having this direction of velocity, and you are imagining something here, for example another object maybe, and you are going to find that one. So, but this one in a future time will come. Currently maybe this one is here and it is also moving. Your vehicle is also moving this direction, and then your target is to meet this one after, for example, 5 frames or 10 frames or 1 second or 5 seconds. How can you do that? This is your training pursuit. And another, the opposite of pursuit is this one is going to that position in a future time, and your one can go to that position. This is pursuit, but your one is trying to avoid. This vehicle is trying to avoid that position. Try to make bigger distance from that position. Then we are telling that this is evasion. So do you understand the difference between evasion and, for example, and pursuit related to seek and flee? In seek and flee, we have this target position fixed, and then this is trying to go to that target position. In the future also this is the target position. But in pursuit, we have this position, but this is also moving. So in the future this will be here, and the target of our vehicle or intelligent agent is to go for that position. That is pursuit instead of seek. If you go to this link have some kind of Java applet or something like this. Maybe you cannot see this one in current version of Explorer or Mozilla Firefox. If you want to see applet based things, maybe you have to go to an older version. I don't know, just try the older version of Internet Explorer or something like this. Okay? If you want to see this, but you can actually see this on the video tutorial also. So you don't have to go for those applet things. You can go to this link just to see the explanation. The one I'm telling you now. Now what is arrival? You have a vehicle, it is moving in this direction, this is your target. So now see, you have a car here and you have a target here. The car is, for example, 60 miles per kilometer, per hour it is moving. So from this position you are moving here. So now if you just show in an artificial scenario that the car is just kind of like this, it is not looking realistic. What is the realistic scenario? The realistic scenario is the closer the car is, it will be slowing down. And then when it reaches here, it is just getting the speed 0. You understand that? To make something more realistic, this is we are telling us arrival, how to design that one. When something coming closer, it will be making its speed lesser. That is the idea. This is arrival. So this is kind of seeking behavior, but the only thing is how to slowing down the speed. Then maybe you can ask how to slow down the speed. Do you have any idea how to slow down the speed? For example, your vehicle have maximum speed. It is running with maximum speed in one direction. Let's say by seeking behavior, you already calculated the direction by which it can go from this place to this place with that maximum speed. But you want to slow down the speed because the more closer it is, it should have lesser speed. How can you do that?
Oh, closer you are, the speed gets lower and lower.
Yeah. How will you define that in programming?
Calculating the distance from your vehicle to the target,
Yes.
and then decreasing the, like from the current speed of the vehicle, you take off a portion.
Yeah, that is true. But let's say I'm going from Aalborg to Copenhagen in a graph. Or here you are showing Mohammed is going from Aalborg to Copenhagen. Will I slow down from Aalborg and then continuously slowing down until Copenhagen?
Well, you could have a threshold.
Yeah, that is the thing. These are the when you implement this one practically in programming, then this kind of thing will come in your mind. You cannot do this one like that. That somebody is slowing down from Aalborg. So you have to define a boundary around the target location. That when it comes to this boundary, then it will come to this boundary with its maximum speed. But then it will slow down. Something like this. So these kind of matters you have to consider when implementing this. So now obstacle avoidance. Just see, I don't know what game is this. Maybe some of you can know. So this guy is walking, but there is an obstacle here. If he go in this direction, then we will be stopped by the tree. If he goes this direction, he will be stopped by the wall, something like this. But if you just define a program where he will walk, and this is the scenario, then he will just continuously walk because what we are showing in the pixels with the color, it doesn't matter what kind of calculation is going on with him in his walking. But then you have to define what is obstacle, how far it is, and what will it do when the obstacle comes in front of it. Okay? So let's say this is our vehicle again. This is one obstacle, this is another, and it is going here. Does obstacle avoidance mean that you will keep the average distance, I mean middle path of all these things, just going like this? Does this mean this one? Obstacle avoidance. Do you understand the question? We have three obstacles. You have the vehicle here. For an intelligent agent, you are showing how this agent is moving. Let's say it is a vehicle or car. And these are two obstacles. These are trees in the road or something like this. Or somebody is walking, for example, here. And these are trees here. How will it work? What will be the realistic scenario here? Is that just going like this? In the middle of all these distances?
Not like it's just extend here. It will just move straight until the obstacle comes.
Yeah, that is the answer. If you make this one going just middle of this, just try to imagine this one. You will feel that this is not looking realistic. You understand that? If you move this one in this direction, instead of going like this in this direction and then go like this, it is not looking realistic. Obstacle avoidance means you will continuously go, and there will be a threshold or boundary for every single obstacles. Then when you meet the boundary, you will keep the distance until that boundary. Then you will move little bit and then go like this. If your target is here, you will not go like this. If your target is here, you will just simply go like this. That is more realistic. So while designing AI system or intelligent agent, you have to consider these things. So, do you understand that? Obstacle avoidance. Wandering. What is that? It is also a very simple concept. You have one vehicle here, for example, or one person. Actually, wandering is not that much matching with vehicle. It is more matching with a person walking randomly. Just he is thinking something. Then what are the considerations here for wandering? To make it realistic, instead of just when you see, if you just like, for example, I am a human being, and you design this one in a game environment, I am moving, and if you just make me like this, then it is not realistic. Okay? There should be something realistic, looking like realistic. You wanted to say something?
No, just that the angle is small.
Sorry?
Just that the angle
Yeah.
should stay small.
Yeah. It means that when you put something which is moving randomly, wandering, something, an object which is wandering, you should not just make this one changing very rapidly. Just change little bit. In this frame, it is in this direction. The next frame, it should not be in the opposite direction. Then it is not that much realistic. Of course, it is depending upon what kind of object you are choosing. If it is car cannot be in this direction in one frame, and in the next frame it cannot be in the opposite direction. Human being, I'm not always acting like a soldier that just like this, it is not like this. Human being also just moves slowly. And then sometimes follow a rounded path to move. But sometimes if it is fish, some big fish, they follow something like this. But if it is a small fish, you can see here we have a small aquarium. There are some small fish. These move something like this and then just immediately going back again. So if your intelligent agent is that fish, you are showing something graphically that a fish is moving, then you can consider that it can move just like in the opposite direction also again in the next frame. But if you are showing a car, then that car normally cannot just move in one frame from this direction to that direction. It takes seconds. One frame is, for example, in 30 frames per second case, you are getting 30 different frames in 1 second. But a car needs multiple seconds to move from one direction to another direction sometimes. So while designing intelligent agent, you can consider that one. While designing wandering, do not change the direction so much. Or do not change the speed impractically, which is not looking realistic. Try to change the speed slowly up or slowly down. Try to change the direction slowly left, slowly right, something like this. In one frame it is going right, so keep right in few more frames. In one frame it is going and then go left maybe. I mean, just follow a path which will look more realistic based on your way of defining the agent. What kind of agent you are defining, that will actually set the thing for you. Then path following. If you can remember the example of the car we saw in the video, that was actually following the path. You can define a path, and then you can put your vehicle here which can follow that path. But then again it is coming the question like this: will it follow the path so that it looks like a rail following the line, something like this? You know train line and the way train goes, isn't it? If it looks like that, it will not be realistic maybe in your case. So while path following, when you put path following, it should look like you are walking in a corridor instead of just following a line like this. You understand that? Good. So, yeah. And also, let's say this one is trying to follow this path. Then you are moving the direction maybe in this way. then it can go maybe little bit of this and then come like this. I mean just make it going up and down instead of just following a line directly, so that it looks more realistic. How a real object moves, just try to give that feeling here. And then how will you define that one? That how much this vehicle can fluctuate from that path? You are not following exactly that path. As I am telling that you should not just show that it is kind of an artificial agent which is going just straight in the line like a train following a train line, something like this. No, not like this. You will give a threshold, boundary that okay, this is the road. Within this it will be. How will you define that road? When you show this one, you can say this one as a span. And when you tell this distance, you can tell this one as radius. So you can define this one by these two parameters, a spine and a radius. Okay, guys? Yes?
I just think that it could be easier to, for example, if you're animating something,
Yeah.
to make the path
Yes.
more realistic. So the agent is following a path, but the path is kind of making those things for it.
Yeah.
Do you understand?
I think you were saying about, for example, there is a snake game where the snake is eating something and then it is going larger and then kind of it is following a path and then the snake body is also showing kind of path direction or something like this. Is that like that? Okay, just explain one more time.
You say that it's not natural to follow the path, like just straight, like a train track.
Yes, yes.
But
It is for if you are
make-
making a train, then you should show a train track. Yeah.
But if you're making a human,
Yeah.
and you're trying to make it not look like a train.
Yes.
But what if you just change the train track so that it looks like it's a human walking? Then
Yeah, it is true. But then actually you are putting this radius very low. That is the idea. Okay? So you can make this one in that way. It is true. When you do not have a defined path in front of you. But for the car example, you already have a path. You have shown in the figure that this is the road. The car is going. If the car is always following the middle of the road, then it is looking like artificial.
But it's also,
Huh?
isn't it also simply because we have the wedge body which we apply force to, we aren't just translating it along the path,
Yes.
we just accelerate it.
Yeah.
And it has momentum, right? So it shoots out to the left.
Yeah, that momentum thing is important. Keep that one in mind. And that's why you need radius. Because if you just put this one in this direction, it is not exactly moving here directly. Or you can actually code in that way, but that will look artificial because the real thing has momentum. So it will continue going in that direction little bit more, even if you try to push this one. Inward, yes. So the whole idea of this path following and considering this kind of spine and then radius is just to give realistic look. If you show graphically, it should give a realistic look. If you give an intelligent agent, for example a serving robot, it should not just, in some of the old-fashioned movies, science fiction movies or old-fashioned robots, or still the toy robots, you will see that the robot is moving like this, just straight and then going straight, something like this. You know the Robocop example, he just moved like this, something like this. So these are not realistic. What is realistic? Realistic is you are fluctuating because of the momentum. So to show that fluctuation, you have to actually allow a radius. But to follow the path, you have to follow a spine. That is the idea. Now, containment and wall following. What is that? See, this guy, maybe you want to go this direction and then he will go this way. Then we can say that he is following the wall. Here you can see the wall and one person, and here you can see the similar kind of wall, but with just an unknown object. Your intelligent agent. So what does it mean by containment? It is just looking like fish in the aquarium. The fish go in this direction, but then it moves in the other direction because there is a wall.
But that's not realistic.
That's not realistic for fish. Yeah. So if you agent go and then get bounced here, there are some old-fashioned game, DX ball or something like this. I don't know. Your generation maybe didn't play this. I played this one, and actually last week I played with my child and he didn't like it. So I understood that this is not their taste anymore. So those kind of game actually show that the ball will go here and then bounce back from this place, something like this. But for an intelligent agent, for example, a human being is walking, there is a wall. You cannot just show that the guy just bumped into the wall and then going in the other direction. So that is the thing. What is wall following? You have to keep a specific distance from the wall. You will define that distance. That is the idea. It is just similar as the obstacle avoidance, something like this. And then what is containment? Let's say this is closed area. And then these are some intelligent agent moving inside of this area, just like fish in the aquarium. So normally the fish do not get bounced in the wall. So you have to define a distance from which the fish will move or your object will move, agents will move, something like this. That is the idea of containment. So yeah. Then the last thing for simple behaviors, flow field following. You have agent here, and let's say these are some other agents. You can say like this, or you can say these are, for example, water flowing in this direction, and this is a boat, which is just moving based on the water movement or something like this. So to show this one realistically, what will you do? You will show that the boat is coming, for example, in this direction when starting, but then it is trying to align with the direction of these flows. So you have to make this one moving on the direction of the flow you are defining. Okay? That is the idea. This is also called force field or vector field, if you want to define this one like this. Then how is going about the calculation? You see, this is the vector direction, this is the target direction, and this is steering. It is just kind of seeking again. Yeah, that is flow field following. This is until now before that. So do you have any questions on this? These are the simple behaviors we can consider about an intelligent agent. No question. So then just have a break for 10 minutes and then we will talk again. Okay? Okay, we can start. So we already discussed about the simple behaviors, which are not a combination of multiple behaviors. But now we will go to combination of multiple behaviors, okay? And this is one thing, combination of multiple behaviors. Another thing is, if you have multiple intelligent agents going together, what will happen, how you will define different steering behaviors in relation to each other of these multiple agents. We will discuss this one here. So first we will have some basic grouping concepts, and then we will show the steering behaviors on the few more. What are the basic grouping concepts? The first one is neighborhood concept. When you have an intelligent agent here, let's say this is your vehicle, it is going in this direction with this velocity, then based on your environment and the definition of that intelligent agent, you can show that it can see everything, or you can show that it can see from this point to this position, or you can show that it can see only these positions, something like this. So when you are telling that the neighborhood of this one is with this radius and then this angle, only it can see in front of it, the direction of its velocity. Then if something is running beside this one, it cannot see that. So while calculating or programming the thing, you will not consider what is going on here for this agent, if we define this one as a thing. What is going on here, it will not hamper your calculation. It will not affect your calculation. So this is the thing you are defining, and that's why we are telling that this is the neighborhood definition. If we say that you have two agents, and then you have to keep a specific distance between these two agents, then let's say one agent is here, another one is here. Well, you have some code or script associated with this agent. If you can remember the concept of Unity, for every single agent or object you can have a script, and that object is continuously running that script. So you have one agent here running this script, you have another agent here running another script. Now, if you want to make a distance, keep a distance between these two objects, this object, as its viewing angle is this one, and neighborhood definition is telling that it will have this angle as the viewing angle, and this distance it will cover, so it cannot see anything here. So the script of this object will not do anything to maintain any distance what is lying here. But if you have an object here, the script of this object will keep the distance, because according to the viewing angle, this object can see this one. That's why we need a neighborhood definition. So neighborhood definition is just a concept. When you implement something, you have to keep the neighborhood definition. Then now my question is, do you understand what is neighborhood definition? And how to define this one for an intelligent agent? Again, same two parameters. One is angle and the distance. And which angle? It may be, for example, it is looking towards the direction of its velocity. Sometimes you may see some kind of a strange a creature or something like this, which may have eye in one side. I don't know whether there is something like this. But sometimes you can have intelligent agent, something like this, in a game as a strange creature which may have eye in the back. So then you can move this one. The velocity direction is this, but this one is on the other direction. The things it can see. So the neighborhood definition is the things it can see. And based on those, it will take the decision. So the things it cannot see, it will not consider that one in decision making. When you define an intelligent agent, you have to define its neighborhood. What does it mean? If you say that this one will never come closer to another object, so that the neighborhood can interfere, it means that you are setting this distance as the threshold, so that it will never be closer to any obstacle or another object by crossing this boundary. So when you write a script for this one, the script should write that one. that if there is any other object or obstacle closer to this one, it will go away from that. So that, or if any other object is coming closer, by to cross this boundary, it will just keep away from that one. That is the idea of neighborhood definition. Then what is separation? Separation, if you see multiple objects or multiple agents here, what is separation? First of all, you have to define the neighborhood. What is the neighborhood? Based on the neighborhood, it can consider which are the objects it will consider to define its separation parameter. For example, for this object, this is the neighborhood. So this object will not have any impact on decision making of this one in separation parameter. But what is separation parameter? Separation parameter is telling how closer you can come to those objects, those other objects. How closer you can come. I mean, how much distance you will maintain from the other objects. If you see that this is allowable distance, this will be here. There is no problem. But if you see that this is not allowable distance, this is closer than the allowable distance, then it will go away. This is one way of defining the thing. So you have three objects, position. Let's say this is a graph. These are the positions. And then you can just calculate the distance and then see if the distance is closer, just go away. Move this one in this direction. The steering will be in this direction. Another way is, if you have three of these, calculate the distance and then try to find the average distance of these three distances. If something is closer than the average, then you will just go away from that. Because it means that you are going closer of that agent, which you don't want to. You want to keep separate your agent. So the agent script need to run this kind of code so that it is continuously measuring the distance from the other agents within its neighborhood, and then it will keep the distance. So as this is outside of the neighborhood, it will not have any impact in the script. So do you understand the relationship between the neighborhood definition and this one, separation? If we do not define the neighborhood, or if we do not consider the concept of neighborhood, then what will happen here? Yes?
If you take all of them, all five into account?
Yes, all the five. Let's say there are 5,000 parameters here, or different objects here. You are running a flock. Flock, you understand? Many birds flying together in one direction. Let's say you have so many, and you want to keep the separate distance from each of them. How do you do that? Then you have to define your own boundary. Then it will make it easier for you. Okay? Good. Then what is cohesion? Separation we understood. You are closer. If you are going closer, just keep some distance. How much distance you will define. Based on your threshold, it will go away. That is separation. What is cohesion? Cohesion is, for example, you have 4 here within the neighborhood, and then your vehicle is here, or let's say your vehicle is just closer to here. So now if you consider these things, your vehicle is not maintaining equal distance from the others. Cohesion means showing something which is kind of looking equal or matching to each other. The distance it is maintaining from each other, these two, the distance these two are maintaining, the distance these two are maintaining, there should be some kind of matching. Or it looks like matching with each other. At least you have to create that kind of reality. So how will you do that? We will just consider the center of mass of all those points, and then we'll move this one to center of mass so that it looks that they are having the similar grouping or something like this. For this example, it is not that much clear why it is moving here, because you may consider that the position of this one is still looking good, because this distance and these distances are nearly equal. But still, the cohesion means you will try to keep similar distance so that that looks similar in terms of their environment or surroundings. So you can do this one by calculating average position. And the last concept related to this one is alignment. Your vehicle is this one going in this direction. But if you can remember the concept of flow field or force field we discussed just before the break, then let's say the other, for example, all the fishes are moving like this. Then one fish is moving little bit strange. Then you can see this one. If you show this one graphically, people can understand something is going wrong here. But if you want to show that no, this fish will also move in such a way that people cannot understand that there is something irregularity. In the case of fish moving, for example, then you have to align this one with the other things. But then are they fully aligned? This one, this one, this one? No. That is the practical life scenario. In practical life, we will not see that everything is aligned. But then when you are thinking that you will align this object with the other object, how will you do that? So it means that you will just try to find out an average direction. Average direction. This is moving this direction, this is moving this direction, this is another direction. Find the average direction and then put your one to that average direction. And every single object, if you design this one in Unity, they have their own script and every single object is running that script. It is trying to move to the average direction. Then you will see that this kind of irregularity will be reduced. But then will it follow kind of train is following train line, something like this? No. That's why you always need to consider momentum. When it is trying to move in this direction, then it will have some momentum. And also you will have to put some threshold so that it can move little bit within that. Because 5 bars is going as a flow. And then do you think that all the bars is exactly aligned in every single point? Not like that. Sometimes they can move something like this. That is the reality. So you can put that kind of reality here by just defining a random variable and then randomly move little bit up and down, something like this. Then combined behaviors. It is coming as first as leader following. So leader following is actually taking two things. One is separation, another is arrival. We have a leader here and all of our objects, we are telling that you have to follow the leader. What does that mean? Then let's say all of them are moving also. Then this object is trying to find the leader, but leader is also moving. Then it is kind of persuasion, isn't it? We saw persuade. What is persuade? It is not seeking exactly, it is persuasion. Because if leader is moving, in the next frame the leader will not be here, it will be a bit forward than its current location. So that's why it is kind of persuasion we have to do. Then leader following also need to be what can I tell you? It should be ensured that you are keeping a specific distance or at least a minimal distance while coming closer to follow this one. And then leader is going on, you are also going on. Then what will be your position when you are following a leader? You cannot be in front of the leader, but you cannot just show that this one came to this position just in the next frame. So it will just slowly follow this one, eventually in maybe 1 second of the video. The leader is proceeding and this one is coming like this. And then when this one is coming like this one will also keep some distance so that it can come here. So every single object normally have the behavior combination. How? This one also has separation and neighborhood definition. This one also has separation and neighborhood definition. But what is the target? This one has a target related to pursuit. This one has another target related to pursuit. So when it is trying to reach the target, in the same time, it is fleeing from this one if they are coming together or coming closer. So when you consider the steering behaviors, fleeing, pursuit, or evasion, something like this, all these concepts are coming when you are considering this kind of group behaviors. When multiple objects you have to consider like this. What is crowd path following then? Crowd path following is kind of, what can I tell? I think here I can give a good example. Let's say this is a path, or this is a door. We are intelligent agent, maybe artificially created. We want to go out of this door from this room. That is the idea. Then what is crowd path following? So if somebody tell that just go out from this room, then he can start going out. What will I do? I will also start going out like this. Maybe I was in this direction walking, but when I hear this command, then I will slowly move here and then I will start going like this. Then crowd path following has some other challenges. If I go there, the door is small, but we have so many objects. What will you do? Then still the same concept will come. I have to keep my neighborhood concept. I have to keep the separation, and also the direction will look like it is kind of cohesive. The other it is also, you can think about force field following, something like this. I mean, this kind of concept then you have to put together if you consider crowd path following. Then what is collision avoidance? Obstacle avoidance, we saw this one, isn't that? Obstacle avoidance. There is a, for example, tree, and this guy want to walk here in this direction, then there is obstacle. So he has to avoid this obstacle. But what is collision avoidance? We have two intelligent agents. This one going from this place to this place, this direction. This one is going from this place to this direction. In the future time, it will be here and this will be here. There can be either overlapping or a collision. Overlapping of the neighborhood or collision. What will they do? So your agent need to calculate that if there are some other agent with this velocity in the environment, then what will be the future position of that agent within my neighborhood? Then if it seems that I will collide with him, then I have to follow another route so that I will not collide with him. Something like this. That is the idea. So you see here, it can start, put the steering like this, well, and then this one can put the steering like this, so that they will not collide anymore. Which way you will put the steering, it is actually your choice. Maybe instead of colliding here, they can just go here and then follow the same path, like as leader following. Something like this. What will you define and which way, how much angle you will define here, it is depending upon what you want to do in the next. What your object will do in the next. So I think we have two more. One is queuing, another one is flopping. So what is queuing? as just keep the same example that we want to go out of this room by this door, or just here, all of these are coming here together and want to go in this path. What will happen? If they come closer, they will see that only two can go together maybe. But then rest of the agents need to slow down and also keep the separation. That is the idea in queuing. So it will have seeking. Seeking means the target is going in this direction, so it is going to this target, that is seeking. But then it will have containment. It will not go outside of this direction, any of these, because it is going in this direction. And then it will have separation. They will not collide with each other, even though they are trying to go in this direction. So if they don't want to collide with each other, and if there is no space, if this object want to go this way, but there is no space because of these two objects, then it needs to slow down. That is the idea. So the code example script you have to write in that way, that if there is something in front of it and in the seeking direction, then it will slow down, creating a space for the others. And the last one is flocking. If all of these are intelligent agents, can you understand what kind of behavior they should show? To show something looking like real. If every single of these things are intelligent agent, every single of these shifts, the behavior it will show, that is the flocking behavior we want in steering concept. So that will keep alignment. Alignment means, you see, maybe some of this sheep is little bit, for example, maybe some of this sheep is little bit, this one is showing this direction, this one is showing this direction, but the flow as a whole together is going in this direction. So what is alignment? Every single of this sheep is actually trying to follow the flow direction, but they need space, they need time to move in this direction. That's why they are still in this direction. That is the thing. We have to keep the alignment concept here, and then we have to keep the cohesion concept. If, for example, here this one is not properly cohere with the others, this is a practical scenario. That's why you can see this kind of hole. But in most of the agents are following that one, that they have a specific distance, not more, not less, something like this. That is coherence. And then still they are not overlapping on each other. I mean, one ship is not going up of another ship, not like this. So this is separation. These three concepts, if you put together, then you can get a flocking concept. So these are the steering behaviors defined by Renault in his paper, and I have discussed these behaviors in front of you so that you can feel what actually intelligent agent do in its environment, and which we can show as a realistic environment. Now, when you see a car as an intelligent agent moving on a track, you normally feel that car is not the movement of that car. If you give a realistic image, if you give a realistic road, you will see that many of the games today or many of the videos today is showing you a very realistic movement of the car, even though you know that movement is calculated. How do they make these realistic movements? They consider this kind of steering behaviors we have discussed. Put the concepts in the code, and then we see that this is looking very real. But the number of concepts related to steering behavior are not so many. We have discussed nearly all of them here. So the number of concepts are not so many. When you put the separation concept, it is done for that object. It will always keep separated from the other objects. When you give the leader following concept to one object, it will always follow the leader. Just write the script for the leader following concept. Then how will we write the script? As I told you at the beginning, we have to define each of our object with some of the parameters. What will be its maximum speed? What will be its minimum speed? Or minimum speed actually can be 0 if it is reaching a target. And then what will be the mass? What is the direction? And then what is the target direction? And what is the current direction? Something like this. Based on that, by applying some vector geometry, we can calculate that one. So the last step, when we calculate the force of steering, our vehicle is moving in this direction, but our target is there. So there will be a force which we will calculate by applying the steering behaviors. And then that force will move our vehicle to this direction. Not immediately, it will follow a slow path to show this one realistic by considering the concept of momentum. So I want to show you some example, but before that, just see this one, locomotion. When we calculate that force and put this one on an actual physical device, or put this one on an agent which we are showing graphically, then we are telling that this is the step of locomotion. It is actually taking our force as signal and then showing this one practically, what is happening. So if you can recall, I should have actually put that figure here. If you can recall, we had three things. One is action selection, another is steering, and third one is locomotion. First is action selection. I am here, I need to go there. So this is seeking. Then I need to go there. This is my action selection. And then when I define steering, what kind of steering I have to go? This is seeking steering behavior I have to follow here. Then I will seek that position. And then the last thing is, when you calculate the force to seek that position, then you will apply that force on a physical device or an artificial device in a graphical mode. And then that is we are telling locomotion. This is the whole definition of defining steering behavior in an artificial agent. Just see a good example here. The behaviors I have discussed in front of you, you can see some example here. Yeah. See the names. Each of these are artificial agents, and they are following that separation concept, neighborhood concept, all these concepts. You see, the whole idea behind this lecture related to steering behavior is just giving you the idea that how some simple behaviors can give you a whole realistic loop in AI. Everything we can see in a game or in any complex AI system which is looking, which is visible to us, and we feel that this is looking very realistic, is actually using these concepts. And they are giving very natural look or something like this to us. So you see these things, and now in practice time, I will recommend you to see this, to follow these tutorials. One is steering behavior in Python, how to implement that one. From the very basic, they try to show that one, so you will understand that. Okay, because you have the idea what is steering behavior, and you have the complexity of thinking, what kind of matters you have to look while looking for steering behavior. That is important. The complexity you have to keep in your mind when you are seeking what options you have to consider. It is velocity. When you are seeking, then also you have to consider arrival behavior, that in arrival you have to slow down. All these matters when you have in your mind, then it will be easy to implement this one in programming by using some vector geometry. And then the next thing, after finishing the steering behavior experiment, when you do in your own practice, then you will go for GUI programming in Python. I think you didn't do this one before. So you can just have some idea how to use graphical user interface in Python. Okay. Then this is a series, Car AI with Unity3D. They have the Unity project example also, how to make something, a car is moving realistically, something like this, how to do that from the beginning. Okay. So the steering behavior we are discussing about, a car is not a group object, okay? A car is normally not a group object. Well, in realistic scenario, maybe in a highway you have multiple cars, but when we are showing here, it is not a group object. It is just, there is a path and then we have only one object, that is car. And then we can have obstacles, we have wall following, something like this. Then the last thing you will see, how to bind Python with Unity3D. I mean, in Unity, if you can remember, you can write a script in JavaScript language and C#, something like this. So they do not support Python directly. So there are multiple ways to do. IronPython, this is a library, you can use that. Or another way can be, let's just discuss another way, the developer. And the third way, just making a TCP server, where the Unity script will work as a server and Python script will work as a client, and then, or Python script will work as a server, Unity script will work as a client. When there is something, the position of the object, the velocity, mass, everything will be sent to Python program, and then Python program will calculate the next steering mode, and then send this one to Unity, and Unity will calculate, will just show this one in practice. You can do all these things in C#, you can do all these things in JavaScript also, and maybe you are familiar with these languages, but you can do these things in Python. You may ask why we need Python for doing this. Normally you don't need, maybe for this example, But if you can learn this one from this simple example, it will help you to do something bigger in Python and then put this one directly in the Unity. Okay? So in practice time, just look into this. If you get stuck in any place, just write me or stop by my office, we will discuss. Then you have a target. And target is assignment 3. I told you to play with A star search. And I requested you just spend some time so that you can solve A star search. I don't know whether you got the fully workable A star search in your machine by your own, but I also uploaded an example in, I think, in the last lecture maybe. If you just run that one, it will run. It is kind of string searching or something like this. I cannot remember. If I do not upload, I will upload today. Okay? You didn't find that. Okay, so I will upload that.
Slides and the competition results from that.
Okay, then I will upload one more link. Okay, just a Python file which have the implementation of A star search. Just go into the code. If some of you already implemented, very nice. If you cannot implement, go into the code. Try to realize what is going on there. Okay, but that example will not directly match with what we need in the assignment. Because we are not searching text here. We are searching on a maybe pixel by pixel basis, a path finding, something like this. So you have to match. But the basic algorithm is same. Okay? So what is the assignment? You must make a star search and a steering demonstration. That is the assignment. And then you have to fill up some of the conditions. Just make a map of, for example, 1000 tiles. As you can see in the video, as you saw in the video, there is a space and the object is moving on the space and showing some steering behaviors. So divide the space into tiles, let's say pixels, 1000 by 1000 tiles, and you can give the tiles in Unity design. You can put the tiles as a terrain. Maybe there are some hilly area, there are some ground area, something like this. And then based on that, you can put some cost value with each of the block, and then you will have 4 to 6 different types of tiles in the terrain, and then you will make 10 non-flying creatures. Non-flying means the creatures you saw in the video, something, just 10. Make 10. You can make more, but I don't encourage that one. But you cannot make less. Okay. At least 10 different intelligent agents will be on the board. The board will be 1000 tiles, and then the tiles will have different path cost. And for example, this is the starting point in the board, and then if I click mouse on another point, this will use A star searching algorithm, and then all these intelligent agents will go to that position by following group behavior. You understand that? That is the idea to do. Okay? And then what will be the submission material? You will make a video, and while you will just show that how the packs are moving. I mean, all of these 10 objects are moving from one place to another place when you are clicking the mouse in another place. You are clicking here, they are going there. You are clicking here, they are coming here. By using A star search, shortest path algorithm. Okay? So yes, and then you will give explanation how you implemented A star search, and then how the steering code is working in your project. You can make the video, let's say 3 to 4 minutes long. Okay, and then this will the whole submission will keep a zip file, which is including the implementation in Unity and the link of the video. Just see an example here how it will look like. Just say this is an intelligent agent, and if the guy is clicking mouse, and then it is going to find the shortest path from its current location to the mouse position, and then going there. You understand that? Then maybe you see here, based on different colors in the tiles, you can just put different path costs, something like this, and give it a realistic look. Instead of giving this kind of tiles and artificial look, just give a natural terrain, tree or something like this. And your object should be non-flying. So do not give a fly over the tree and then reaching there. Can you finish? Good then.
We'll find out.
Yeah.